Good morning, ladies and gentlemen. It's indeed a pleasure and an honor to present to you this morning to such a distinguished audience. And the title of my presentation is Breakthroughs in Drilling Technology. And in follow-up to what Brian said in his opening comments, what I would like to address is this popular misconception that what we do in oil field drilling is really just about brute force and brawn. And you've seen a lot so far in terms of what's done at the surface, and what I'd like to do is take you downhole. I'd like to demonstrate to you the technology that is used downhole, which not everybody is aware of what is actually going on in terms of being able to achieve some of these wells that we want to drill. But before I do that, let me press the right button. I'd just like to share with you a few details regarding the Schlumberger organization. So Schlumberger is an oil field service company. We're not an oil company. We provide services to oil companies, and our goal is to support the oil companies in terms of finding and developing oil and gas hydrocarbons. So the way we're structured in Schlumberger is we are essentially broken up into three disciplines which very much reflect the focus of our clients. The first one is in drilling, as in how do we drill the wells and access the hydrocarbons. The second one is in terms of characterization. How do we characterize the subsurface and understand the reservoir? And then the third is in production. And what I would like to share with you today is what we do on the drilling side of that equation. So we're around 120,000 employees. We believe that one of our key differentiators, our competitive differentiation, is the diversity of our workforce. We have about 140 nationalities, and we operate in over 80 countries. We have a revenue stream in the order of $40 billion, and our R&D spend on an annual basis is in the order of $1 billion, of which on the drilling side, about a third of that is spent on drilling technology. So that encompasses 6 research labs around the world and multiple engineering and manufacturing facilities. Specific to Texas, we have over 12,000 employees here in Texas. We have 3 engineering centers, and we have operating bases in Houston, Midland, Dallas, and San Antonio. I'd also like to say that I believe that we're also the industry leader in 3-letter acronyms. And I've done my best to try and remove most of those acronyms throughout this presentation, but you'll have to forgive me because I'm sure a couple have slipped in here. So, let me talk about the industry as a whole. The reason why technology is so important for the oil and gas industry is that producing oil and gas in complex environment is getting harder and harder as the challenges in terms of the geology, geography, and the geometry of the wells that we drill are getting more complex. So the industry fosters a risk-taking attitude, and by risk I'm not talking about safety risk, I'm talking about risk associated with finding and developing hydrocarbons in an economical fashion. And so the technology has a key part to play in this in terms of mitigating the risk and pushing the barriers of the types of wells we can drill. So what do we mean by complex and challenging? Well, I think you've seen from some of the earlier presentations today some of the challenges we face, but let me put this into perspective for you. As we get into more challenging geologies and logistics, the environment that we work in becomes much harder. So typically, the wells that we drill today are up to about 150 degrees C at the bottom hole temperature. We're dealing in pressures in the order of 20,000 psi. We're having to pump fluid into the tools downhole at around 800 gallons per minute. But those limits are being pushed. In the Gulf of Mexico, we're now talking about wells at 200 degrees centigrade. We're talking about downhole pressures in the order of 40,000 psi. You've seen on earlier slides the issue of the cost of some of these deep water wells, and just to put that in perspective, the average run rate for a deep water rig is in order of $1 million per day. So from a service company perspective, this puts a huge onus on us because the reliability and the service quality that we provide can have a huge impact on the financials for our clients. If you think about a deep water rig drilling at, say, 30,000, 20,000 feet, if something fails in the bottom hole assembly, then essentially you have to trip that out of the hole. And if you have to trip out of the hole, that can take you 1 day to trip out and 1 day to trip back in. So that's $2 million. And that could just be a fuse, a capacitor, a chip, or something in the tool that's failed. So reliability and service quality is paramount. So I think you all know what a drilling rig is by now. What I'd like to do is put it in the context of where it fits into our business. So the drilling rig is the drilling machine. It is the part of the process that rotates the drill pipe, which in turn rotates the drill bit. And then at the surface, we pump drilling fluid, otherwise known as mud, into the drill string. It passes through the bit, it keeps the bit cool, and it carries the cuttings to the surface. So it lifts the cuttings, it prevents blowouts, it actually seals permeable zones within the formation. And it is also used as a primary source of power, as a means to generate power for the tools that are downhole. So what is our contribution? What exactly do we do as Schlumberger in this process? So on the drilling side, we provide all the equipment downhole that is necessary to orchestrate the actions of the drilling rig. So it's the products and services that allow us to do that, as well as obviously the expertise to operate the equipment and the modeling and prediction capabilities to really understand how the system should be performing and how it does perform. So why is this such a big issue? Well, I think in the early days of drilling, when you just used to drill vertical wells in a field, then it maybe wasn't that big an issue. But as we drill more complex wells, both in terms of geology and in terms of geometry, the interdependencies of what's actually happening within this drilling system become more and more complex. We have to better understand the interaction of the drill bit with the rock, the interaction of the drill string with the well bore, the drilling dynamics associated with the tools, and how that all links back to the drilling machine at the surface. So what I'd like to share with you now is I'm going to go back to those two major challenges that I talked about in terms of geometry, and then I'm going to talk about geology. So in terms of geometry, I wanted to give you this as an example. What you've got plotted here is what we call the dog nose plot. And this is a plot of what we call extended reach wells. These are wells that have a high ratio of vertical depth versus horizontal displacement. You can imagine the challenge of the geometry of a well, that you can only drill a certain distance down, a short distance down, but you want to get a long way away from where you start. So that in itself means that you've got to have high build rates within the well, but at the same time that means that by putting a high bend in there, you can't actually get that far. So what you've got on this plot is you can see on the vertical axis that you have a series of wells in the order of 500 to 1,000 feet in terms of depth, and then going out in the order of 30,000 to 40,000 feet. So you can, and by the way, the targets that you're talking about to land these wells are about the size of this room, so in terms of the height. So you're talking 10, 20, 30 feet, but you're starting 30, 40,000 feet away, which is in the order of 5 miles away. So you can see where the records sit today. ExxonMobil holds the world record with the work done in Sakhalin on the east coast of Russia. And the real challenge here is how do you precisely control that geometry such that you can push this piece of spaghetti all the way out to 30, 40,000 feet. Looking forward, these are some of the projects that are on the radar screen. You can see work out in Qatar at 50,000 feet, and the industry believes that within the next 10 years, we're going to be out at 55, 57,000 feet. To put that in perspective, for those of you who live in the Dallas region, I just made this plot to show if you started drilling from the center of Dallas where you could end up in terms of drilling one of these wells. And based upon my experience yesterday commuting from the airport to here, I think you might actually find you can drill there faster than you can actually drive there. So the second challenge, that's the geometrical challenge. That gives you a flavor of the geometrical challenge. In terms of the geology challenge, when an oil company plans a well, obviously the geologist is involved, and the first thing he'll say is, we've got this huge reservoir, it's beautiful, it's a nice pancake, you can't miss it, off we go. So the first thing we have to do is we have to plan the well, and as I say, we're looking at in the order of 30, 40 feet if it's a good reservoir, and remember, we're starting 5 miles away from this. So we have to have some specific targets that we're given. So the first target will be, how do we hit the reservoir? The second target then is, how do we land the well in the right sweet spot in the reservoir? And then the third target is, actually, how far can we go within the reservoir? So that's the ideal world. The reality is it looks something like this, right? So it's not a pancake. It's faulted, it's lensed out, and we need to be able to see this in real time and be able to actually respond to those changes such that we can actually steer the well and keep it in the reservoir. Obviously, the more feet we have in the reservoir, the more production we get. So now let me talk about the key components that we provide to address those two risks or those two challenges that we face. Let me start off with the drill bit. So this is obviously the piece that actually cuts the rock, something that is a fundamental part of the drilling operation. Today, the industry has moved to what we call, most of the drilling that we do in the high-tier market is using what we call fixed cutter bits. It's using polycrystalline diamond compact cutters. And over the last 10 years, this technology has moved a long way. When it was first introduced, it could only really drill homogeneous type formations because if it hit a hard stringer, the cutters would break off. But now, due to developments in the technology, these bits can now drill very heterogeneous type formations. So when we plan the drilling of a well, the first thing we need to do is to match the cutters with the formation. So we have, if you could click the first animation for me, please. So what we do is we do a series of scratch tests for different cutters on different formations such that we can understand how aggressively the cutter will work, the depth of cut we would get with the cutter for a particular formation, and what sort of dullness or abrasivity that we would get on the cutters. Because remember, that bit had better last, because if we're coming out the hole because the bit fails, that's another $2 million. So once we've determined which is the right cutter for the right formation, we can then model the bit itself. And if you could click on the second animation for me. So what we do now is we will build a bit profile whereby we are building this to ensure that we have the best bit for both the steerability and the stability of how we drill. And the stability is very important, because if the bit's wobbling around all over the place, it's going to create huge shocks and vibrations within the drill string. And remember that little capacitor I told you that may fail and have to pull out the hole? That will definitely do it for you. The third step, if you could click on the third animation for me, please, is now we've modeled the interaction between the bit and the formation, is we actually model the whole drill string dynamics. And here we model all the side forces and the torsional effects that are on the whole drill string from the bit all the way to the surface, to make sure that we haven't created something that's actually going to create more bad than good in terms of shock and vibration. So that's the drill bit. The second part is, how do we actually steer this thing now? So in the old days, the way that we used to steer the bottom hole assembly was quite simply, we would put a bend into the drill string. And what that meant was, by orientating that bend, we essentially orientate the bit. So the bend is at the bottom here, we'll drill up. If the bend's at the side here, we go to the left. However, the problem with that is, if you've got a bend in the drill string, you can't rotate the whole drill string, right? So what you have to do is you have to put a motor below the bend such that only the bit is rotating and the drill string is actually stationary, because you want to point the bend in a consistent direction. The challenge with that is, and the limitation of that is, because you're not rotating the drill string, you're not reducing the friction in the wellbore along the drill string. So your axial friction along the drill string is very high. So you're sort of pushing against the friction. So you haven't got a cat in hell's chance of drilling one of those extended reach wells because you just can't push it far enough. The only way you can drill extended reach wells is if you rotate the whole drill string. That has a challenge because I can't do it with a bend. So how do I actually steer that bit while rotating the whole drill string? So this is when we came up with the concept of rotary steerables. So rotary steerables is a concept whereby you're able to rotate the whole drill string, but are able to steer the bit in a given direction. And the way this is done is that you have a tool downhole that has a geostationary platform within it, such that even though you're rotating the whole drill string, the actual sensors know exactly where you are in space. The concept I'm going to show you here is what you call a push-the-bit rotary steerable system. And what you have is you have pads on the outside of the tool which are synchronized such that if you want to push the bit upwards, then your geostationary platform will tell you when the pad should push on the low side of the hole. And so it synchronizes. This thing is rotating about 120, 130 RPM. So 120 times a minute, the pad will come out and it'll push on the low side of the hole. If I want to go up, if I want to go down, then I will set the tool such that the pad will push at in sync on the top side of the hole. So why are rotary steerables so important? So what I'm going to show you is a schematic now of how a horizontal well would look, how it would be drilled historically and where we are today. So historically, you would drill as much vertical section of the well as possible because it's easiest to do a vertical well than it is a horizontal well. Then you would pull that out of the hole and go in with another bottom hole assembly to drill the curved section. And now I'm talking about using bent subs and motors, yeah? You drill the curved section, then you have to pull that out of the hole and change it for another bottom hole assembly to drill the lateral section. So you can see on this time depth plot, you have these flat spots where it's non-productive time, where you're just tripping out the hole to change the bottom hole assemblies. With rotary steerables, the first generation of rotary steerables, we're able to actually drill the curve all in one go. But the challenge of the early generation of rotary steerables is we didn't have enough directional aggressivity in the tools to allow us to get the same sort of build rates as you could with the old technology, which meant that you would have to kick off earlier, higher up, you have to do more directional work, and you can see the well actually lands in a later part of the reservoir. However, with the latest generation of rotary steerables that are out there now, we can actually drill the same profile of well as with the old technology, kicking off later and entering the reservoir, obviously, earlier. Earlier in the reservoir means more pay. And of course, with the rotary steerables, because you're rotating the whole drill string all the time, the distance you can go laterally is significantly greater. So let me now talk quickly about the measurements themselves. So all of this is fine and dandy, all these fancy tools downhole, but how do you actually know what is happening? And what are the measurements that you need? So the industry has come a long way in terms of the measurement capabilities downhole. And what we use them for are for understanding the formation, the pressure, is the oil and gas present, how much oil and gas is present. So we have directional measurements downhole of magnetometers and inclinometers. We have sonic and ultrasonic measurements downhole to give us geomechanical properties of the formation. We have electromagnetic measurements downhole to tell us the resistivity of the formation, so we can tell if it's oil, gas, or water. We have nuclear measurements downhole to tell us about the porosity and the density of the formation. And we also have magnetic resonance technology to tell us about, again, the pore space and the fluid mobility. So all this technology is sitting within a sub in the drill string. And again, don't forget, those fuses and those capacitors, they can't fail. And they're providing this data in real time as we're drilling. So we have putting this in perspective, you take an outcrop and you plot the bottom hole assembly on it, you can see, we talked earlier about the seismic measurements that we get from surface, and they give you this sort of level of resolution, hundreds of feet. We then have electromagnetic measurements that can look around, they're azimuthal measurements that can look around the drill string, and they can tell us about where the boundaries are, whether they're up, down, or below, and how many boundaries that exist. We then have the formation evaluation measurements, which actually then tell us within a short radius of the wellbore what are the actual properties of the formation, the density, the porosity, the fluid content, etc. And then right at the front, we have high-resolution electromagnetic resistivity measurements that provide us with images of the formation. So here we actually can see the fractures and the dip of the formation, and it gives us a warning of how the formation is changing direction as we steer through it. To get the data to surface, there is no cable, right? The way we get the data to surface is we take advantage of the mud. And what we do is we create a pressure wave within the mud through a siren-type technique, a stator and a rotor, and we create a pressure wave which, by changing the speed of the siren, we can change the frequency of the carrier wave, and that frequency shift is what gives us ones and zeros that we can then decode into engineering units. So the technology has moved a long way. When first these logging while drilling measurements came out, each one would be in a separate sub, and you'd end up with hundreds and hundreds of feet of these measurements if you wanted to use them all. We're now in a position where we have a single sub, a 30-foot collar, that has in the order of 20 measurements, which provide essentially the full spectrum of what I explained on the earlier slide. As well as the formation evaluation aspect of what we do with the measurements, I come back to my pancake reservoir versus the faulted reservoir. We use the real-time measurements to actually tell us how the reservoir is looking as we're drilling so that we can actually steer the well. So what you see here is an image of a resistivity log that is taken in real time when you're drilling. The dark areas are shale, the yellow areas are sand. So as I'm drilling, I'm getting an azimuthal reading. It's looking above, below, left and right, and it's telling me if I've got boundaries of sand and shale above or below me, and the directional driller can now steer to make sure that we optimize the time we spend in the sand sections. So in conclusion, the challenges for the oil and gas industry are definitely increasing as there is a growing need to access more complex reservoirs and environments, and therefore our industry relies on rapid technology evolution. Service quality and reliability are a prerequisite to operating in these types of environments. And that is something that we strive to really differentiate ourselves on versus our competition. And so it's a very exciting industry because the formation, evaluation, measurements, and drilling technology that is required is evolving at a very fast rate. Thank you very much.
With this technology, how about reworking old fields? Is this being done?
Yes, definitely.
I think of the shallow cable tool drilling and straight down, and the well's not producing any longer. It seems to me this would be a logical extension.
Yeah, there's a clear market opportunity in terms of what we call re-entry drilling, where you go in and you actually cut windows in the casing of an old well, and
right.
You actually come out and you find the bypassed oil that is there.
Thank you.
How do you keep weight on the bit when you're out 60,000 feet? Is it just the weight of the pipe that's pushing at the end, or is it?
Exactly, and that's one of the reasons why there comes a point where you cannot actually drill any further. So you have to be very smart in terms of how you configure the pipe and where you actually put your heaviest pipe, such that you optimize getting the weight to the bit. But by rotating the pipe, you obviously reduce the axial friction so you can get the weight to the bit. But if you've got to slide the pipe, then you just, there's no way you can get the weight to the bit.